Okay. So let's see this. So let's see this one first. So this one equals this size on the left-hand side. Okay, G stands for the gas pressure, right? So this equals. What does this one tell us? So this tells us the pollutant removed from gas equals the pollutant will transfer from gas to liquid, right? So pollutant removed from gas equals pollutant gain by liquid. Okay, so this equation tells us the pollutants removed from gas equals the pollutant gain by liquid. Let me write this one time. Okay? So seconds, student, please highlight this. This is area for the mass transfer. This is area for mass transfer. So the small letter A is the area per unit volume of packing. Write this one down. The small a stands for the area per unit volume of packing. And capital A is a cross-sectional area of column. Cross-sectional area of column. Will 给你们这一页吗? Do I give you this page? Yes, right. Okay. Because I saw some students take photo, I didn't give this page. And DZ, student, DZ is the small height differential, right? DZ is the small height of the tower. So DZ is the small height of the tower. Ni is mass transfer flux. Ni is mass transfer flux. Ni equal dc over dt. Ky is overall gas phase mass transfer coefficient. Y stand for the gas phase pollutant mole fractions. And this one is the actual. Without the studs. This one is the actual. Okay, with studs. This one means equilibrium. This one means equilibrium gas phase mole fractions. Okay? So it creates, so Y minus Y studs. What is this? So this actually the driving force. The Y minus Y stud y minus y star, actually, it creates a gradient, right? It creates a gradient. This is the driving force for absorption. This is the driving force for absorption. Okay, so y should be larger. In this case, y should be larger than y stars. Okay, if y is pretty much close to y star, that means the driving force is very weak. This absorption, the driving force for this absorption is very weak. Is y is close to y stars. All right? And y equals, the capital Y equals small letter y, the mole fraction, over y minus y. Student, this is so-called mole ratio. This is mole ratio. So y is the pressure over pressures. This is partial pressure. The T here stands for total. So y equal the partial pressure of the pollutant. This is the partial pressures of pollutant. I'm sorry, pen is not used. This is not a book. Okay, the capital Y is the partial pressure of pollutant over the total pressure. Okay, I hope you guys familiar with this so-called log mean value. Okay, log mean value. So after that, we can obtain. Okay, what we need is Z equals, okay, here. Okay, this is what we need. Okay, this is the design equations. Okay, this is the design equations. Student 9-53 is the design equations. Okay, and this is the most important one. Okay, so this equation means, okay, the higher tau, how tall you need to build for this. So the ZT is the tau height. The ZT is tau height. And HOG, this is the height of an overall gas transfer unit. Okay, and NG, this is the numbers. This is number of overall gas transfer units. Okay? Calculation is not a problem. Okay? If you have test script, you just plug in those data, right? The problem is, what the physical meanings, the meaning of those terminologies, okay, the meaning of those parameters. Okay, the first one, NOG, what does this tell us? This tells us how difficult the separation is. The physical meanings, 物理意义, the physical meaning of NOG tells us how difficult the separation is. So, how about HLG, the 10 HLG? HLG tells us how effective the packing and mass transfer are. So NOG tells us how difficult the separation is. HOG tells us how effective the effectiveness, how effective the packing and mass transfer are. Therefore, if NOG is very big, that means the removal of pollutant is difficult. So if NOG is very big, that means this removal is very difficult. If HOG is very big, that means your packing is full. You need to change or you need to reset the packing. Okay, student. And NOG can be calculated by using this formula. NOG can be calculated by using this formula. And HOG so HOG equals HG plus A times HR. Okay. HOG equals HG plus A times HR. Okay, so let's see NOG first. Okay, the M here, I want to mention the M. The M here is the stop of equilibrium curve. And this defines, this defined by Henry's law. Okay, because Y star equals M times X star. Okay? Then HOG, O stand for, O here stand for overall. So HOG is the overall gas phase heights. Okay? So the G, so HOG is the overall gas phase height. And G stands for gas phase height. Okay? A is not area. A is absorption factor. A is absorption factors. Okay, A is absorption factor here. A is absorption factor. And HL, L stands for liquid. So HLO is liquid phase height. Okay? Okay, let's do this question. Okay, let's do example 9-10. Okay, I might give similar questions from the textbook, but just change the value. Okay, I might give the similar, but change the value. So you need to be familiar with the question in textbook, okay? So, in this question, the question asks us to determine the height of the PEG towel. Okay, the purpose for this PEG towel is to reduce ammonia in air. Okay, from a concentration of 0.1 kilogram per meter cubic. Okay, from this, reduce from this to this. Okay, and the given data is diameters, temperatures, pressures, Hg, HL, and QL, QG, QL. From QG, QL, what you can get? You can get A, right? Okay. A equal M QG QL, right? The A here is not area, okay? A equals M times QG over QL. M is the slope. M is slope, okay? So please calculate these questions. 9-10, okay? I'll give you 2 minutes to think about it. So I'm going to give you 2 minutes to think about it. Okay, who has the textbook? Please raise your hand. What was the question? Sorry? Louder? M. M what? Okay, I think I should give you M. M equals 1 point. Okay, let me give you M. M equals 1.068. Okay, 1.068. Okay, let me give you M directly. M equals 1.068. Okay. Yeah, I think you with this information, I think you can do it. Okay, hands up. Did I give you a solution for this question? 我有给解答吗 ？No, okay. But this is from textbook. Okay, that's good. Okay, first off, let's find out the molecular weight of ammonia. Molecular ammonia is 17, around 17. Okay, and air is around 28.9. How to calculate this? Okay, so we're gonna assume we have 0.80%. So 0.8 times 28 plus 0.2. We have 80% of nitrogen, 20% of oxygen, right? So 0.8 times 28 plus 0.2 times 32. Then you will get something around this value. Okay, so this is the molecular weight of air. Molecular weight of air. Okay, and the density is around this. It's around this at 25 degrees Celsius. Okay, from the textbook. But the problem is the operation temperature is 20. Okay, so we need to do some correlation. Okay, so we need to do some correlation. So this is for 25 degrees Celsius, right? And this one is for, so it's 25 plus 273. This is 20 plus 273. So we need to correlate. We need to adjust. Okay, we need to correct the density. Understand? So the real density, okay, the density at 20 degrees Celsius. So this is the density at 20 degrees Celsius. It's around 1.2. Okay, after that, let's calculate Y1. Okay, so the Y1 is for inlet gas. Okay, let's calculate Y1. Y1 is for inlet gas. So we got this amount. Okay, in the same manner, we can find out Y2. Student, Y2 is for outlet gas. Put it right down. Y2 is for outlet gas. Okay? And because the incoming liquid, the entering water contain no ammonia. So X2 is 0. Okay, so you need Y1, you need Y2, you need X2. Everyone okay? Everyone okay? Y1 is inlet gas, Y2 is outlet gas. Okay, X2 is for the entering water because at that stage, the entering waters has no ammonia. So X2 is 0. Everyone okay? All right? Okay, the next we want to find out the M. How to find out M? Based on Henry's law, Y star equals MX star. Therefore, M equals Y star over X star. So Y star is the equilibrium mole fractions of ammonia in gas phase. So this is equilibrium in gas phase. And X is the equilibrium mole fraction of ammonia in liquid phase. Okay, so what do we have? Okay, we have at pressures, okay, for the pressure of ammonia 15.199. Okay, this one got 15 kilogram ammonia per 100 kilogram hydrogen. Okay, so we can use this data, student, we can use this data to calculate Y star. Okay, we can use this pressure, ammonia pressure, the pressure of ammonia data, okay, to calculate Y star. We can use this to calculate Y star. Okay, and use this, the amount of ammonia in water. Okay, the amount of ammonia in water. I think this is H2O, not H2O. Student, this is H2O, not H2O. Please write this one down. This is H2O, not H2. So we can use this to calculate S star. Okay, we can use this to calculate Y star, use this to calculate X star. Okay, so the Y stars equals P ammonia over P total. P ammonia over P total. Okay, Y star equal P ammonia over P total. So this equals 15.199 over 101 point, so in 1 hemisphere, right, 325. So this is what we got 0.1500. Okay, this is H2O, not H2O. So S stars how to calculate S star? Okay, so S star can be calculated from this for 15 kilogram. We can use this one. For 15 kilogram ammonia per 1 kilogram water, right? So first of all, we can calculate the moles of ammonia first. So mole ammonia equal 15 over 17. Mole ammonia equal 15 over 17 kilogram. Okay. And moles of water equals 100 over, because 100 kilogram, right? So it's 100 over 18. Okay, so it's 15 kilogram in 100 kilogram water. 15 kilogram ammonia in 100 kilogram water. So mole of ammonia is 15 kilogram, okay, over 100 kilograms. Okay, so the mole fraction will be 15 over 17. 15 over 17 plus, because the denominator will be total, right? 15 over 100 over 18. Okay, we got something like 0.1369 here. So n equals y star over x star. So equal 0.1500 over 0.1369. So equals 1.068. Please write this one down. Everyone okay? Okay, sorry, I forgot to give you this data, okay? And also this is water, okay? This is water. This is water. 那个笔注你可不可以贴个麦给我一下，我去改。
好。
Sometimes when I keep tell myself I need to correct those error, but when I go back, I forgot where should I correct. Okay. Okay, so after that, let's find out A. So A is based on this formula, right? A equals M over. So we can find out A. So A equals M times QG over QL. QG and QL are given. M is what we just calculate out. Okay. So then we find the A. Okay, after that, plugging all the data, we find a G. Okay, and we can also find out the HG. Then use the formula ZT equal NOG times HOG. ZT equals NOG times HOG. Okay, so then we find out ZT equals around 7.8. But you should build something larger than this. Okay, not too high. But if below this, this absorption tower is useless. Okay, so you need to build above this height. But you don't need to build like 9, 10, okay? Because all of those building material cost money, okay? So you can build like 8. Okay, so if your boss, okay, asks you to build an absorption tower, right? Then you need to do this calculation and tell him you need to build at least 8 meter height. Okay, to be effective, remove those ammonia. Okay, if you just build like 7, then the effectiveness will be pretty good. Okay, so you need at least 8. Okay, at least 6.6, 7.6, right? Just make it integers. Then you will say, oh, I'll build 8. Okay, so this question is for packing, right? Second one is for trade. Okay, this going to tell you how many stage or how many tray you need. How many stage or how many trays you need for this absorption tower. So in this case, you need at least 1, 2, 3, 4, 5. You need at least 5 trays. Okay. Okay, you can draw by drawing this. Okay, by drawing this, this tells us you need at least 5 trays. At least 5 trays. Okay, so the gas enter in the bottom, okay, and liquids flow from the top. Okay, the liquid phase enters at the top. And these lines, the purple lines represent something called operating lines. Okay, what does operating line mean? Okay, the operating lines means the mass balance. This operating line represents the mass balance between gas and liquid. These operating lines represent the mass balance between gas and liquid. Okay? And this blue lines is called equilibrium lines. Okay, so this equilibrium line shows the relationship between y and x. Between y and x when gas and liquid are in equilibrium. Okay, these blue lines tell us the relationship between y and x when gas and liquids are in equilibrium. So at equilibrium, there's no net mass transfer, okay? And also keep this one in mind, the operating lines must occur above equilibrium lines. Operating lines must occur above equilibrium lines. Okay? Then you will cause the driving force of absorption. Okay, after that we start to draw. After that we start to draw those staircase. Okay, after that we start to draw those staircase. After that we start to draw those staircase. One staircase means one train. Okay, that means one ideal, spherical, ideal train. Ideal train. One staircase represents one ideal or spherical train stage. So there are 5, right? There are 5, right? This means you need to build at least 5 trains in your absorption tower. For this case. Okay, so you have 5, so you need at least 5 ideal trips. Okay, have you learned this in unit operation yet? 学过了嘛，对不对？ Okay. So, operating lines must above equilibrium lines. They start to draw this staircase. One staircase means one theoretical or one ideal train or stage. So in this case, we can draw 5. We can draw 5 staircases. That means it needs this absorption tower need at least 5 trains or 5 stages. Okay, to remove, for example, like ammonia. Understand? Okay, let's have. We still got lots of things to mention. Okay, let's just have a 5-minute short break. If you want to go washroom, please go washroom now. Okay, so the break will be 3:10 to 3:15. Okay, only 5 minutes. Now, 你在跟我玩速读。没有说不抄了。哎，这考不好会把你拿掉。